Welcome back to the deep dive. So if you're building or even just thinking about these really complex AI systems, you know the magic isn't just the language model itself.
Oh, not at
It's
all.
in the pipes, the architecture, all the wiring that makes the model actually functional and, scalable.
Right.
Today, we're stripping those layers back. We're doing a deep dive into the Model Context Protocol, or MCP, and specifically the design patterns that give these systems their structure.
And it's really the difference between having, say, a brilliant brain
Right.
and having an organized corporation built around that brain. For you, listening, these patterns are just crucial.
They're like blueprints.
They are. They're architectural blueprints that show us how different needs get met efficiently. We're not just defining terms today, we're getting at the why. Why you'd pick one blueprint over another.
And what the trade-offs are, that's the mission. We're treating MCP as this foundational protocol, and everything we discuss now are the tested, battle-hardened ways to plug real functionality into it.
Exactly. We'll start simple and then build up the complexity. Let's start with how these systems talk to the outside world.
Okay, integration and workflow management. So the first blueprint we see is, I think, the most straightforward one.
The direct API wrapper pattern.
The direct API wrapper, yeah. This is really the quick fix, isn't it? It just takes an existing API and puts a standard MCP interface around it.
It is the simplest point of entry, and, there's a huge appeal to that speed. The source material really underscores that this pattern is ideal for quick integrations.
Right, when you're dealing with an API that's already established and stable.
Exactly. You don't waste time rebuilding anything. You just standardize the handshake, the communication. If you need to, I don't know, check the weather or get a single stock quote, this is perfect.
But I immediately see a risk there. I mean, it's fast, but doesn't that create a really rigid relationship?
How so?
Well, if that external API provider changes something or gets rid of a function, you have this direct one-to-one dependency. Your wrapper could just break instantly.
That is the critical insight. Yes. Speed comes at the cost of rigidity. So if you need something more robust or your task needs more than just one single API call, you have to level up.
And that's where we get to the composite service pattern.
Right. And this is where it starts to get really interesting.
This feels like the difference between asking one person for one thing versus coordinating a whole team for a big project.
Precisely. The composite service pattern is all about orchestration. It's designed for more advanced functionality by making multiple different APIs work together in a single workflow.
So like placing an online order.
Perfect example. You have to check inventory, that's API 1, then you process the payment, API 2, then you dispatch logistics, API 3. A single MCP process manages that entire coordinated dance.
Okay, so we've gone from the quick kind of brittle wrapper to this more robust composite service. But what if one of those steps, like you said, checking inventory, takes like 10 minutes?
A long-running task.
Yeah, if the system has to wait for each step, the whole thing just grinds to a halt. Which I guess brings us to our third foundational pattern.
The event-driven integration pattern. This is the architect's answer to the problem of waiting.
It enables non-blocking workflows.
Right. So to put it simply for you listening, the system doesn't just sit there frozen waiting for an answer. It publishes a request, the event, and then immediately moves on.
And it only picks up the result when the other system signals back that it's done.
Exactly. The events are published and processed asynchronously in the background.
That idea of asynchronously is so fundamental to modern scaling. So the main application stays fast and responsive while the heavy lifting happens backstage.
It's essential. The event-driven pattern is for any AI system that has to handle these really long-running tasks or, ingest huge volumes of data without creating a bottleneck.
You decouple the task from the processing.
And you maximize your system's throughput. It's all about maintaining a good user experience.
Okay, so that covers getting data in and structuring the workflows. But now, if we do all that, we've got a system that can handle huge amounts of data and complex workflows. If we try to funnel all of that back to one single central AI model, the whole thing becomes a mess. We need to talk modularity. We need specialists.
And if we connect that to the bigger picture, modularity is just essential for scaling intelligence itself. This is where the general MCP to agent pattern comes in.
So we stop asking the main brain to do everything.
We start delegating. This pattern is all about invoking these specialized agents within the architecture, specifically for complex reasoning or decision-making.
So the core MCP just routes a request, like analyze this customer sentiment, to a specialized sentiment agent instead of doing it itself. What's the big architectural win there?
The advantage is resilience and sort of intellectual purity. This modular approach is the key to scaling and refining the architecture. You can improve your planning agent without breaking your scheduling agent,
You can swap out a weak specialist for a better one.
without rewriting your core system. It keeps the main architecture lean and the specialists focused on doing their one job brilliantly.
That makes a ton of sense for broad scaling. But in the real world, especially in some industries, you don't just need a specialist. You need one who's operating under really strict domain-specific rules.
And that leads us right to the next layer of refinement, the domain-level MCP to agent pattern. This isn't just about having specialists, it's about structuring them.
You're putting them into a formal hierarchy.
Exactly. We're organizing those specialists into defined departments or domains, so to speak.
So if the general agent pattern gives us a team of experts, the domain-level pattern gives us, what, a corporate org chart with middle management?
That is a fantastic way to put it. This pattern structures agents hierarchically, and that enables crucial domain-specific control and management.
And this would be for high-risk or regulated areas.
Totally. What are the examples we see where this is just non-negotiable?
I'm thinking things like complex customer service flows where you have to make certain legal disclosures, or payment processing.
Yes, especially payment processing. By isolating these high-stakes functions into domain-level agents, you can apply specialized rules, audit logs, security protocols, things that would be overkill for the rest of the system. It's control through isolation.
So scale is handled by the general agent pattern, and then targeted compliance and control are handled by the domain-level pattern. That's a very elegant structure for managing intelligence.
It is. But we still have one last, really crucial pattern that addresses a basic reality of deployment.
Which is?
Sometimes the network connection just isn't there.
The operational resilience problem. Let's talk about the local resource access pattern.
Right. This one is all about a specific operational need. Not every system lives perfectly in the cloud. You could be on an oil rig or a remote factory, or even just an edge device in a retail store with terrible Wi-Fi.
So this is the bad Wi-Fi pattern.
Basically, yeah. It's about ensuring the AI system doesn't just become a brick when the internet drops. This pattern is essential for fast, local access to files or databases or whatever it needs to function.
So it's about operational continuity.
It is. When you have limited or no connectivity, you have to be able to access resources locally and quickly. It maintains speed and ensures the core function continues, even if it can't phone home.
And the trade-off there is you might sacrifice real-time global consistency for that local resilience.
That's the trade-off inherent in that design.
Exactly. Okay, let's pull this all together. This really is a complete toolkit for an AI system designer.
We started with integration. We had the direct API wrapper for speed, even though it's a bit rigid.
Right. Then we moved to the composite service for that complex multi-step orchestration.
And we solved the waiting problem with the event-driven pattern for big data volumes and, that non-blocking processing.
Then we got into organizing the intelligence itself, the general agent pattern to delegate reasoning, which is critical for scaling.
And we refined that with the domain-level agent pattern to build a hierarchy for specific control and compliance, like in payment processing.
And finally, we addressed the real-world environment with the local resource access pattern, making sure the system works even when connectivity fails.
It's a powerful illustration of flexibility.
The overall message here is that MCP gives you a whole variety of design patterns to structure these systems effectively. And for you, the listener, you have to look at your specific needs, speed, complexity, compliance, and then choose the right design pattern for the job.
Absolutely. The choice of pattern dictates the system's performance, its cost, and its resilience. It is the highest level of architectural decision-making you can make.
That's a phenomenal summary.
Yeah.
Now, as we always do, we want to leave you with something to chew on, something that pulls together the implications here.
Okay. So we've established that the event-driven pattern handles massive data volume, and the domain-level agent pattern handles specialized control and compliance. So here's the thought. If the primary goal of these patterns is optimization and structure, how might combining them fundamentally change things?
Go on.
What if you combine the event-driven pattern for huge data volumes with the domain-level agent for specialized control? Think about a huge organization processing complex data streams, like payment processing. How does that combination change the actual speed at which they can operate and innovate?
A powerful thought. You've been diving deep with us into the architecture of tomorrow. We'll see you next time.